Good day, Sir Bal. Good day, classmate. My name is Ismael Sigalanto, and I'm the reporter 20, and my topic is periodic motion experiment. Describe the condition for resonance. So, what is periodic motion? Periodic motion is a type of motion that repeats itself in equal intervals of time. This means that the motion follows a predictable pattern that keeps repeating over and over. So the key characteristic of the periodic motion is periodic, or T, is the time taken to complete one full cycle of the motion. Frequency, or F, is the number of cycles completed per unit of time. It's the reciprocal of the period. F equals 1 over T. The amplitude is the maximum displacement of the equilibrium position. So here's some example of periodic motion. Simple harmonic motion, or SHM, a special type of periodic motion where a restoring force is directly proportional to the displacement from the equilibrium position. Example, including a mass on a spring, a pendulum, and a vibrating tuning fork. Circular motion. The motion is an object in a circular path at a constant speed. Orbital motion. The motion of celestial bodies like planets and satellites in their orbits. Wave motion. The proportion of disturbance through a medium like sound wave and water wave. Visual representation of periodic motion. Periodic motion is a fundamental concept in physics and has application in various fields, including mechanics, acoustics, optics, and electronics. So, what is resonance? Resonance occurs when the frequency of an external force or vibrating system machine that natural frequency of another system, this causes the second system to vibrate with a significantly increased amplitude. The key condition for resonance. So first, matching frequencies. The frequency of the external force or vibrating system must be equal or very close to the natural frequency of the second system. Continuous energy input. The external force or system must continuously supply energy to maintain the oscillations of the second system. So let me describe to you what is the two conditions for resonance. So first, matching frequencies. Natural frequency. Every physical system, whether it's a pendulum, a bridge, or electrical circuit, has a natural frequency at which it vibrates when disturbed. This frequency depends on the system's physical properties such as mass, stiffness, and length. Dividing frequency. This is the frequency of the external force or vibration that is applied to the system. Resonance occurs when the driven frequency matches the natural frequency of the system at this point. The system absorbs energy from the driving force of the maximum efficiency, leading to a dramatic increase in the amplitude of its oscillation. Energy and oscillation will diminish, however, will continuously. Continuous energy input. Energy transfer for resonance to occur when mass continuous supply of energy from driving force to the system. This energy is used to overcome the system internal damping force, which tend to dissipate energy and reduce the amplitude of oscillation. Sustained oscillations. If the energy input is insufficient, the system will eventually lose energy and the oscillation will diminish. However, with a continuous supply of the energy at the resonance frequency, the oscillation can be sustained or even amplified. So here are some examples of resonance. A swing. Pushing a swing is its natural frequency, the rhythm at which it naturally swing back and forth, make it swing higher and higher. A sounding tuning fork. When you strike a tuning fork, it vibrates at its natural frequency. If you hold it near another identical tuning fork, the second fork will start to vibrate due to resonance. A shattering glass. A powerful sound wave at the glass natural frequency can cause it to vibrate violently, potentially leading to breakage. Electrical circuit. In the electrical circuit, resonance occurs when inductive and capacitive reactances cancel each other out allowing maximum current to flow at the specific frequency. So, let me show you a video example.
This video shows the topic of resonance and forced vibrations as covered in the engineering option of IB Physics. To demonstrate, we'll be using a tuning fork and another tuning fork with the same fundamental frequency to show how when one is struck on this rubber actuator and vibrates at its fundamental frequency, the vibration can be sent through the air molecules to the second tuning fork, causing that fork to also vibrate at its fundamental frequency. We'll begin by striking this tuning fork on the rubber actuator. Then, holding the forks close together so that the other tuning fork has a chance to come in contact with the air molecules being vibrated by the first fork. After that, we'll silence the first fork and listen very carefully for the vibrations of the second one. Let's begin.
Understanding resonance. Natural frequency. Every object has a natural frequency at which it vibrates when it's stirred. Amplitude. The size or extent of a vibration or oscillation. Energy transfer. Resonance allows efficient energy transfer from the external force of system to the second system. Application of resonance. Musical instrument. Resonance is used to amplify sound in instruments like guitar and violin. Radio and television. Resonance is used to tune into specific radio or television frequencies. Medical imaging. Magnetic resonance imaging or MRI use resonance to create a detailed image of the human body. Dangers of resonance. Structural damage. Resonance can use structural damage to buildings and bridges if not accounted for in their design. Equipment failure. Machinery can fail due to resonance if it is subject to vibration at its natural frequency. In conclusion, resonance is a powerful phenomenon that can be both beneficial and destructive. Understanding the conditions for resonance is crucial in various fields from engineering and physics to music and architecture. By carefully considering the natural frequencies of the system and controlling the energy input, we can harness the power of resonance for constructive purposes or mitigate its potential negative effect.